Now we'll see store instruction. Okay, so store R1 100 of R2. That means the effective address here is 100 plus content of R2, where we have to store value which is stored in R1. Correct. So we need two registers now, R1 and R2. Assume that, let's say, R1's content is 50, R2's content is 70. Then finally, what is the effective memory address? 100 plus content of R2, correct? 170. Then here we are going to store the data which is nothing but 50, correct? Let us do that. For that, you tell me as a human being, forget about that control memory or control unit, how to use this input lines and how to use this output lines and input line. Do we need any input line? Because we don't require it. Why? Because we are not storing the result into register. We are storing the result into or value into memory. That's why this is irrelevant. We don't supply anything to that. Okay. But we need data from the registers. That's why these two are for output. Correct. That's fine. What we do is we connect one here R1 and we connect another one here R1 R2. So what is going to happen, we'll see. So R1, which is nothing but 50, will come here, but do you want to do addition for 50? No. That's why don't connect here R1. Think about it in that way. So finally we have to connect them such a way that this ALU should be done. That means ALU should be used appropriately. We are going to do ALU between 100 and 70 content of R2. That's why we can connect here R2, right? So R2. So finally we have to provide the register R2's address here and we have to provide here R1's address. When you do that, what is going to happen? Then the content of R1 will be passed here, which is nothing but content of R1 is 50. 50 will come here. Second thing, 100 plus R2. What is R2? Content of R2 70. 70 will be passed here. So slowly 70 will come here. So 70 is must. Now here immediate value will be taken. So immediate value is 100, correct? So through the register that 100 will be taken and 100 plus 70 will be added and you get 170. So finally you remember always this arithmetic logic unit is going to give either the computation for add instructions, that means the result of add instruction or shift instruction, whatever. Otherwise it is going to give you memory address, right? So example for load instruction and store instruction, it is going to provide memory address, remember. So finally this arithmetic logic unit can be used for doing arithmetic for arithmetic instructions, otherwise for arithmetic for load and store instructions, correct? Here there is arithmetic that will be done by ALU in the stage number 3, and let us recall the stages. This is stage number 2. This is, see, up to arithmetic, this is stage number 3, correct? So we can mark it as stage number 3. Then after arithmetic we will be doing this selection of data, right? So that will be in stage number 4, correct? So let us divide up to this point as stage 4. We know that. Now after that the result whatever comes from this RY, that will be stored back to register. Sometimes that will be in stage 5. So this is stage 5 and stage 5, okay? So here to here stage 5. This is stage 2. This is stage 3, this is stage 4. In that way, we can systematically divide our work into 5 stages. So here stage number 1 is not visible because stage number 1 is separate. So in stage number 1, we need different circuitry, remember it, okay? So fetching the instruction and updating the program counter is work of stage number 1. We will see that later. At this moment, we are just seeing the execution part, I can say, right? Stage number 2 to stage number 5. Now, so see this 170, if you see here, that will be stored in this register. After that, in the next step, what happens, that 170 will go like this, correct? So what is that? It is memory address. See, memory address. So 170 is memory address. Now this 170 is connected to your main memory. That means main memory contains a interface here. So that is, let's say, memory interface. So the job of memory interface is whenever someone provides a memory address, then bringing the data, okay? That means going there. This is the memory address. Now since it is a store instruction, this time we are not taking the data from this memory location, we will be storing there, correct? That's why this time, so we have to inform that, my dear memory interface, this time our instruction is writing, please write. Then memory interface asks, yes, I can write. Where I have to write? See, I am providing the address. Then memory interface will ask you, please provide data also. Then sir, where is the data then? What to store? 50, right? So where is 50? Now go back again. So 50 is, see, here you connected that 50 content of R1 here, right? That means second address line. So it will come like this slowly, eventually it will come here. After that, see here. However, this 50 is not selected through this multiplexer, but there is a bypass, you see. It will be passed like this. When you are executing store instruction, slowly this 50 will come like this, right? Now it will stay here for some time. After that, whenever time comes, see it is, see, this is the flow, okay, but how to use this flow properly, how to really get the right data at right time will be done by control memory and timing circuit. Okay, we will see the timing signals. So two things are important. One is timing, when to get the data and how to get the data. Okay, for the timing signals also important. We will be seeing the timing signals and control signals later, so don't worry about them. Okay, at this moment we have a provision. I am showing that if you design your circuit such a way, then definitely eventually we can get the right data if you properly plan it. See, slowly 50 will come here, right? Now at the right point of time, if you take the data, so you will be getting here. Now for this memory interface, you just tell that, so this time I am writing. So whenever you say you are writing, then memory interface will ask you two things. One is address where we have to write, second one data what to write. Okay, so data you supply and memory address also you supply, correct? Now easily we can understand that in this stage, that's why these temporary registers are specially designed to hold the values which are required for that stage. What is the job of this stage? Stage number 4, writing into the memory, correct? So that's why writing into the memory we are doing in stage number 4. The buffers between stage number 3 and stage number 4. See, this is one buffer, this is one buffer. That buffers are going to help us to hold the data, correct? That's why, so though we have data 50 here, which is in stage number 2, we simply moved that to stage number 4, correct? We simply moved it, right, propagated. So that's why this extra buffer is required. The special purpose of this register is what? To just hold the data, correct? Now already we are holding that 50 here, but still we are holding here. Why? Because here the job is done by this stage number 4. So stage number 4, if you design such a way that always stage number 4 takes the data from the registers which are just before the, otherwise between the stage 4 and stage 3, if you plan such a way, then really that would be good. Okay, we will see that because the advantage comes when you do pipelining. That's why this entire foundation is for pipelining. In pipelining you realize that whenever you have the required data in the registers which are located in between the stages, then that would be really good. Okay, so from now onwards you remember between the stages, stage 1, stage 2, stage 3, stage 4, we are going to have temporary registers to remember, otherwise hold the data which is required to do the computation in that particular stage. Example, you want to do some computation in stage number 3, then you need some data, right, that we have to hold in the registers between S2 to S3. Here also we are doing the same thing, you see. To do the computation of storing the result into the memory, we are holding the data into that registers in between the stages, correct? So that is the right thing. We will see that how, because we will see that why, because in pipelining we will be using it extensively. Now finally what is going to happen? So if somehow if you take this data, memory data, right? Now the memory address comes from this cable. Somehow if you take it, then properly we can store the data. So this circuit is going to help you to do the store instruction. Sir, in the gate exam what they ask, just understand it, that's it. Okay, how the things are working. Then if you know that circuits work like this, then automatically you can answer any gate question for sure. They ask very easy questions and they are very fundamental. If you know basics of design of circuits, otherwise the flow of the circuits, the data path of the circuits, then easily we can solve any question. Okay, don't worry. Now we will see, we understood how store will be done. Now sir, what about storing in register? For this instruction we don't store anything into the register. That's why what is going to happen, you see this multiplexer in that. So this is for what? Taking the data 170. Are you going to store 170? No. Are you going to store return address? No. But that 50 here nothing. So that means there is no purpose. That means we don't use it, right? So that's why in the register file we don't store anything. So that step is unnecessary. Sir, but data will flow, right? We have to control it. That's why there will be, I can say, there will be a signal such a way that this multiplexer will be disabled. We have to disable that multiplexer so that it will not work, and it will not send the data to register file. We can plan it. Okay, that is a separate issue. But at least you are now learning that. So how this circuit, the small circuit, is going to do load instruction, store instruction, and add instruction, everything, correct?